All right, so this video is going to be on basically some properties of benzene. So first off, the structure of benzene. We know what benzene looks like already. We've seen it a million times by now. But just benzene is an aromatic compound, and that's really just a name that it was given to it because it smelled, right? So aromatic things, they smell, right? And I guess it's more or less like a misnomer that kind of stuck with it. But it's an aromatic compound that doesn't undergo addition reactions like normal alkenes. So it's kind of fancy because it has particularly good stability. So for example, this alkene with Br2 undergoes addition of that Br2, right? So if we have benzene with Br2, nothing happens at all. Okay. Now, it does actually react. It's not just completely inert, but we have to add some other stuff. So we can do Br2 with FeBr3. So this iron complex is a Lewis acid, and this is required for benzene to react with bromine. But what happens is you get bromine added to the benzene ring, but we lost a proton. So it's actually a substitution, not an addition reaction, okay? It's actually called electrophilic aromatic substitution. We'll get to that later. But we also know that benzene has 4 degrees of unsaturation, right? Done this plenty of times as well, so we won't do that. And it also has resonance for days. So remember, we've got pi bonds, 3 pi bonds in there, right? Let me draw this better. Okay. And if we just drew arrows to draw resonance structures, we can really just go in circles over and over and over and over again, right? And so if we were going to draw a hybrid structure, oh my gosh, my dog, are you serious? We draw a dotted line. We can also draw just solid lines. You might see a benzene ring with that solid line circle in there, and that's representing the same thing. It's because of the resonance structures that it has, right? And that's actually what contributes to its stability as well, which we can get to later. But just to kind of go over some more features of it, the bond length. So that our typical like single bond is 153 picometers. A pi bond is 134 picometers, and benzene. Sorry, let me get this structure not terrible. Benzene has a bond length of 139 picometers. Okay. And that's not just at that double bond that we have it drawn here. It's actually every single bond. They're all 139 picometers. And that's, again, because we can draw resonance structures, right? And the average is really what the structure looks like. They're all the same length, 139, which is closer to the secondary or the pi bond than it is the single bond, right? We also know that this benzene ring is sp2. Every single carbon in it is sp2 hybridized, right? So what does that really look like? More or less alluding to its stability, right? I'm trying to draw a benzene ring slightly angled for you. And we have the top part of that p orbital. I'll draw the bottom part blue. It's starting to look pretty. Oof, looking good. And we know that these p orbitals overlap, and that's what creates a pi bond. But notice there's a bunch of them all in a ring, perfectly overlapping, right? So that's the nature of this sp2 hybridized carbons, but they're all in a ring at 120 degree angles, so it's lined up perfectly to have 6 adjacent p orbitals, okay? And this is conjugation, right? Or they are conjugated at least, and because we have 3 or more, we have at least 3, I guess I should say, and this is what contributes to benzene's stability. Okay, so these lots of pi electrons also make it nucleophilic, right? And that's why it can undergo reactions with electrophiles like bromine. Okay, it just needed a Lewis acid to get the party started though. Okay. All right, so let's move on to nomenclature, right? So we're just cruising through this stuff because we already know this. Like, we're pros at this for sure. So we're probably even good with this nomenclature stuff. But I'll just briefly cover it. The first part we want to do is monosubstituted benzenes, and then we'll go over some disubstituted and polysubstituted as well. So monosubstituted means that there's only one thing on the benzene ring. That's not a hydrogen, okay? And what we want to do is we want to name the substituent and then add the word benzene. Oh my god, it's so hard, right? So hard. Okay, so then we will do, let's just stick with 3 structures here for you. Okay, so we have ethyl benzene. Okay, what do you think the second one is? Oh, I dropped my ice cream cone. Bummer. Isopropyl benzene. Okay, and then we have bromobenzene. I'm not even sure why I have an ice cream cone while I'm recording my voice right now, but you know how we do. So that's pretty chill, right? So the thing about benzene is that we do have common names, so of course, right? And so when we've got a methyl on that benzene, when we have an OH on that benzene, like a hydroxyl, or when we have, let me move this over for you because we're going to need room for the name, or when we have an NH2, an amine, like an amino benzene, right? So the common name for the methyl on there is, that's a toluene. We have phenol, so the OL is like alcohol, and then aniline is when you have the NH2. So these are common names, and you're going to want to remember these because they will be used very often, okay? We probably already have used them. And di-substituted benzenes, okay? So when it comes to naming things with 2 things on the benzene, that's going to introduce the idea of ortho, meta, and para, which we already have, I know, because I felt the need to introduce it sooner, but it is in this chapter, so I'll bring it up again. Okay, so let's say we have 2 bromines on there. We've got different positions that we can put these bromines to give us 3 different isomers, right? There's 3 different constitutional isomers, so we need to figure out how to distinguish between them. And they are all technically going to have the suffix dibromobenzene, if you want to call it a suffix. So I'll go ahead and copy and paste that because, yeah. But now what we need to do is number things like normal, right? So 1, 2. And the 1,2-dibromobenzene can also be called ortho-dibromobenzene, okay? So it's getting a little congested here. Okay, let me move that guy. Sorry. That's the perfect time to eat some of your ice cream cone while you're moving stuff around. All right, so the 1,3-dibromobenzene is also going to be called meta-dibromobenzene. Sorry. Boom, bada bing, bada boom. All right, so the last one is going to be 1,4-dibromobenzene, okay? And this is also going to be known as para-dibromobenzene. So what we'll say is like, oh, that's an ortho-substituted benzene ring, or a meta or a para-substituted benzene ring, okay? That's kind of like the way that you would use the words or the phrase, other than actually saying like meta-dibromobenzene. It's just I don't know. It's kind of like it's useful because like if you're saying like, oh well, this proton in the NMR, that's the meta proton, or that's the ortho proton, or that's the para proton. Like that's also another way we might use it, and so it is useful other than kind of being redundant and naming like a 1, 2, and an ortho, but so it is useful, okay? If we have 2 different groups, okay, so what we want to do to name them is just apply ABC order, right? We want to alphabetize them. And so let's say we have bromine and fluorine, okay? So we have a bromo, and then we also have a fluoro. So B comes before F, and so we have bromo, fluoro, benzene. Super chill, right? Like this stuff is, why can't OChem always be this easy, y'all? Because then it wouldn't be as fun. I'm sorry. I forgot to tell you, hold on, sorry. The ortho, the meta, and the para can be abbreviated as an O, M, or P. So in this case, the bromine and the fluorine are ortho to one another, so you just put O, bromofluorobenzene, okay? Another little fun fact. me eat my ice cream cone while I draw things out for you. Y'all think I'm joking too. If you really know me, you know I'm not. All right, so we've got a nitro group and we have a chloro group. Okay, so they are para to one another. So we have para, chloro, nitro, benzene. Boom. Pretty easy stuff, right? Okay, so if we're using a common name when we are naming a benzene ring, then what we want to do is basically name the compound as if it were like a derivative of that common name, okay? And so what we mean by that is, let me just draw out a couple of examples. So remember that the NH2 on a benzene ring is aniline, right? So let's say we have a NH2 on there, and then we have a bromine on there. Okay, so what we want to do is remember that it's the meta position, the 1,3, meta, bromo, aniline. Boom. Pretty chill, right? Yeah, this ice cream cone was a bad idea. Sorry. I don't like listening to people talk while they eat. My apologies. But this stuff is real chill. So we have a nitro at the meta position. Now we should change that. Let me put it at the ortho position. So we've got ortho, nitro, toluene. So this actually brings up some really fun stuff. So what I want to do here, I'm going to draw out something else for you. So we got a toluene. Let's throw 3 nitros on there. What you talking about, Jess? 1, 2, 3. What is this going to be called? Okay, so it's going to be called trinitrotoluene, right? We got 3 nitros on there, so it's trinitrotoluene. Sorry, we gotta do the, what is that, 2, 4, 6 trinitrotoluene. Really, what I really wanted to point out though was the T, the N, and the T, y'all. You know what I'm saying? Like Shaq, Kenny. But yeah, that's the compound that is TNT, or dynamite. Pretty neat, right? Okay, so was that anticlimactic? Because there was explosions and stuff, and I feel like y'all weren't as excited as you should have been. But remember, yeah, it's TNT. It's dynamite. TNT. And I'll win the fight. Polysubstituted benzenes, y'all. So we've got a methyl, a bromine, and a chlorine, right? So the method, or the like rules for naming these are, of course, you want to give the lowest possible number, so that the set of numbers that you get is the lowest. Okay, so you'll see what I mean by that in a second. We also want to put them in ABC order, and then if part of the ring is a common name, then we want to again just have them be derivatives of that common benzene ring. Okay, so like the methyl group here, right? That's a toluene. Okay, so that's going to be a chloro and a bromo. We also want to make sure that we're assigning that substituent that makes it a common benzene ring, like, or a common thing, like the methyl. That should be labeled as carbon number 1, no matter what. Okay, so in this case, it would be a 1, 2 for the bromine, and then 5 for the chlorine. If we went the other way, what we would get is a 1, 3 for the chlorine, and then 6 for the bromine. So 1, 2, 5 is a smaller set of numbers than a 1, 3, 6. Does that make sense? Hopefully. That's what that first rule means, okay? So now what we want to do is label toluene. We don't have to give it a number because we know that it's implied that toluene gets the lowest number assigned to it, to that carbon at least. And then after that, we have 2 bromo, 5 chloro toluene. And that's all she wrote. That's it. Okay, so let's try some other ones. Okay, so we've got, here's a benzene ring. Let's throw some stuff on here. What do we want? So let's throw an ethyl. Might as well throw another ethyl on there, and then a bromine. Sorry, I'm sticking with the bromine. Um, since we have an ethyl and then an ethyl, we can add those two together and make it a diethyl. Okay, and remember when we have that prefix di, we still go based off of the E in ethyl for our ABC order. We have a bromo, and then we want to try and figure out the numbering. So it's 1, 2, 4. So if you go the other route, starting with the top ethyl, it doesn't work out that well. Check for yourself. 1, 2, 4 is the lowest set of numbers that we can get. And so we make our 4 bromo, B comes before E, 1, 2 diethylbenzene. All right, so that's pretty much, I should have done another one with different letters so that I can really hammer in there that D in diethyl is not included in the ABC order, but I think you guys got that. So let's name a benzene as a substituent. So what does that mean? Basically, when it's a benzene hanging off of a parent chain of some sort, right? So we've mentioned this before. Benzene can be abbreviated as a PH, which is a phenyl. Okay, and not only do we have phenols, but we have this guy right here where we have a sp3 carbon in between. That is a BZ. Remember? Oh, sorry. Let me make that better. Remember what this carbon is called? The sp2 carbon. It's called a benzyl or benzylic position. So that functional group right there is called a benzyl group. Okay, and so collectively this is an aryl group, as well as any of the benzene rings up above. Those are all aryl groups. Okay, just a little bit more nomenclature with that, right? So a lot of this we have kind of talked about before, but now we're actually explicitly stating it, okay, and defining it. Also, it's nice to have that phenyl abbreviation and that BZ abbreviation, because now when we're drawing crazy structures, we can just abbreviate and you guys really understand what's going on. But, okay, so cis 1,2-diphenyl cyclohexane. First draw out the cyclohexane, and then the 1,2 position has a benzene ring on it, right? That's what the diphenyl means, and it's cis, so we draw the wedges, and that's how you draw a benzene ring as a substituent. And based off of the name, or you can go from the name, or from the structure to the name, okay? All right, so let's check out the spectroscopic properties. Again, we should know these already because we're pros at IR as well as NMR, both proton and carbon. Don't let anybody tell you otherwise. Y'all are professionals. So, IR absorptions, proton NMR, and carbon-13 NMR, those are really what we care about. I'm going to go ahead and draw this chart out for you. And you're going to fill in the blanks. If you want, just pause it for a second once we draw this in, and then think about whether or not you know these absorptions, right? Sorry, let me see if I can organize this right here. And really what we want to focus on is the type of CH, right, or carbon, for example, but then also the absorption, so where they're showing up in the IR, proton, and carbon NMR. Okay, pause it, try and fill it out, and blam, that's all of ours, right? So we got the CsP2 hydrogen, the carbon-carbon double bond, etc., etc. So know this chart and where those absorptions are for these, basically their corresponding CH or CC, okay? All right, so some tips and tricks for, what is this? So di-substituted compound, okay? So when it comes to carbon and proton NMR, when we have di-substituted benzenes, there's 3 different arrangements that we can have, and that would be the ortho, the meta, and the para, right? And if we're trying to determine which structure we have, you really want, honestly, you would love to have a di-substituted one because that's really easy, and you can't actually distinguish between ortho and meta, but let me just kind of show you what kind of absorptions we should have, right? So we have the 3 C's and we have the 2 hydrogens, right? Because of the symmetry plane that I've drawn with the red dotted line, that's why but we can draw another symmetry plane for this meta disubstituted bromobenzene. And we have 4 carbons in this case, because they all lie on the plane or on one side of the plane. And we have 1, 2, 3 hydrogens for the same reason. Okay. Now this this para-substituted bromobenzene has 2 planes of symmetry, and so what that actually creates, well, a high amount of symmetry, and all those carbons are equivalent because you can flip this molecule along that plane of symmetry and it gives you the same thing. And so no matter how you flip it, you're going to get 2 carbons, 2 unique carbons, and then from the one with the bromine on it and one without, and then 1 hydrogen. Okay. Now that's not to say that if you had a disubstituted benzene with 2 different groups on it, you wouldn't get a different outcome, because that doesn't give you the same symmetry. Hey, let's say you had a para-substituted, let's say bromotoluene, then you're stoked because that's actually going to give you 2 doublets. So if the symmetry, again, the ortho and the meta, hard to distinguish, but the para-substituted, you're stoked if you get that, okay, as like a possible structure. But that's pretty much it for now. Let me know if you have any questions.